I'm Mike Breen with the American Mathematical Society, and I'm talking with Mark Finney, who was with the U.S. Forest Service at its Rocky Mountain Research Fire Station in Missoula, Montana. And Mark works on studying the spread of fires, trying to simulate wildfires. And so, Mark, can you tell us about that work?
I'd be happy to. So I work at the Missoula Fire Sciences Laboratory, and it's been in operation since 1960. It was one of two laboratories established by the U.S. Forest Service from the late 50s to the 1960s, and it was established because of some major fatality incidents in firefighting. So firefighters were killed, and the Forest Service said, "Look, we need to know more about fires so that we can avoid these kinds of disasters." And so the laboratory, our current laboratory, is the last one. The other one was in Macon, Georgia, and that closed down in the 1990s. But Missoula Lab is still going strong, and we have a number of different research projects there. Some of it's related to ecology, and so the ecological effects of fire and how to use fire in an ecologically beneficial way to sustain our ecosystems. Some of it is more about the fire science or fire physics and understanding how fires behave, and that's kind of what I work on most of the time. We have other people working on smoke production and related projects associated with fire suppression. But my world and my job is mostly taken up with understanding how fires behave, and then also adapting these findings to practical models to use out in the field when we're both planning for fires as well as trying to predict those active fires that are going on now.
And so you mentioned the fire physics and the modeling. Can you tell us what areas of math are involved in that?
Right. So the team that I lead in fire behavior research, we have a number of different kinds of people. Fire research, fire in general, is a very multidisciplinary field because there's no one kind of fire scientist. We have biological scientists, chemistry, physics, engineering, atmospheric scientists. All of those overlap in this little area called fire science. So we have team members that a lot of them are in the physical sciences and in engineering, but we also have electronics engineers, all kinds of engineering, and statisticians, mathematicians, technicians. All of this is necessary to really study fire. There's just no one of us are good at all of those kinds of things. And so the way we study fire behavior is to break it down into its component pieces. We kind of know the basic building blocks, and there are three of them. One is combustion and energy release. The second one is heat transfer. So how does the heat go from what's burning to adjacent fuels that need to then ignite? So ignition is the third one. So you have this coupled system. It goes in a circle: combustion and energy release, heat transfer, and ignition. And then what ignites then goes back and burns again. So this is kind of how we divide up the research problem. And our approach in our laboratory, because we have wind tunnel and combustion labs where we can burn things, and we also do outdoor experiments as well, but is to use experiments to help us understand the phenomenon. We use modeling too, and we use math in a couple of places. One is to analyze the data, of course, and we need that and to come up with mathematical simplifications of the physical phenomenon and to characterize that well. But we also use math in formulating models derived from the experiments that we can use then to predict fire behavior or to understand this coupled system that I described, because you can study the three different component pieces, but until you put them back together again in this system, you can't see the system level behaviors arise, right? Because just burning something in a pile like a campfire or a candle, that doesn't tell you how wildfires use those same processes in spreading. So mathematics and statistics, both of them kind of go hand in hand in a lot of this because we're collecting data. We need to reduce those data down to something that can be analyzed. And then in statistics is a very a useful way of deriving these relationships from a descriptive standpoint. But ultimately, we need to explain the physics. got to explain the physics in a generalized way that we can use for modeling.
And so, for example, would that involve like computational fluid dynamics, or?
Some of our people do that. That's exactly right. If you've ever watched campfires and the flames moving around an awful lot, you know that that's a fluids process, a very buoyant, hot fluid. And so computational fluid dynamics is an area that people use to understand fire behavior, particularly flame behaviors. But we also do simpler kinds of things where we use high-speed imagery of our flames and to capture the movement of flames at very high frame rates. And so image analysis processing is used an awful lot on that. That's not really my specialty, but we also use high-speed infrared cameras an awful lot to take a look at this heat transfer from the flames or from burning fuels to the fuel particles. We can with different lenses and different kind of filters, we can examine the heating of fuel particles as they're exposed to this kind of heat. So when I say fuel particle, I'm talking about pine needles and grasses or pieces of wood, that kind of thing. That's the fuel in wildland fires.
Mm-hmm. And so we've seen a lot of fires in the news, both, it seems like the number of them is increasing, and the intent, the number of big fires seems to increase, or devastating fires seems to have increased too. Do you feel like you have made a lot of recent progress understanding fires?
So we make progress all the time, but I will tell you that some of the earliest questions, the most basic questions about fire behavior, have still yet to be answered. And those the simplest questions are usually hard, but like, how do fires spread? How long do fires burn? Are big fires different than small fires? Do they behave differently? How does live vegetation versus dead vegetation ignite, and does that burn? These are very easy questions to ask, but they still don't have answers to them. So we're still working away on some of these basic ones in the laboratory and in the field. We use the field experiments to see whether or not the relationships we find in the laboratory will scale all the way up to larger fires. So scaling analysis and non-dimensional analysis is used an awful lot. And but when it comes to the very, very biggest fires, they start to become atmospheric phenomena. They involve a very large portion of the atmosphere, and some of the biggest ones can actually become more like thunderstorms than they actually are fires. They're a fire-generated thunderstorm, and it has all of the same characteristics of thunderstorms: lightning, hail, downdrafts, very strong winds near the surface. So it's very difficult to go from the laboratory all the way up to these large atmospheric scales. And so, in fact, you have to actually go take measurements on real large fires in order to do that. And there are people that do that. That's not part of our purview. But no, we're making progress all the time. And of course, we publish our results in scientific journals and present them at conferences, and work with a number of colleagues around the world at our university system in the United States, but also all over Europe, Australia, Canada, even South America. So there are people interested in fires everywhere because it's a global phenomenon. And we have a long history of working on fires and doing fire research in our country. And so we're glad to partner with a lot of the countries that are just starting to develop their research programs.
Now, you mentioned before about, how you're talking a lot about how fires spread. And one thing I remember, like the difference between convection and radiation. Could you tell us a little bit about that? Or as much as you want?
So this falls into the realm of heat transfer, right? And so we had combustion, heat transfer, and ignition. And the questions about heat transfer are still very much unresolved. So for a very long time, for many decades, a lot of scientists had made the assumption not entirely backed up by experiments, but made the assumption that radiation was the principal heat transfer mechanism in wildland fires. And when I say radiation, that is electromagnetic, it's thermal radiation from the thermal band of the spectrum. And it is radiating from the fire or from the flames or from the glowing solid material in the fuel bed. But that radiation is transferred through the air without heating it to impinge on fuel particles adjacent to the fire and heat them up. Now, the issue in wildland fire is that most of our fuel particles are very small. They're the pine needles, they're the grasses, the fine twigs or foliage on shrubs or on trees. And these very fine particles have a unique way of handling radiation. They heat up, the surface heats up from the radiation, but because they're so small, they cool off because they're bathed in the ambient, cold ambient air. They cool off very effectively by convection. Essentially, they suffer from wind chill. Okay, so if you've ever stood out in the wind and the wind is impinging on your body, taking your heat away, well, that's what happens to very fine particles much more efficiently than to us as very large creatures. So the smaller the particle, the thinner the boundary layer is on it. Boundary layer is a thin shell of air that's right next to the particle or to the hard surface. And the thinner that is, the easier it is to disturb it, to move it off. So very thin particles, when the air blows by them, or when they simply heat up and heat the air around them, that is replaced then by cold air, that removes the heat that they absorb by radiation. And so most of our fine particles will remain way too cool to even begin to decompose from the heat, much less ignite from radiation. And this is very easily demonstrated by laboratory experiments. And we have people that have developed models of this, numerical models, where you can calculate the heat transfer inside a particle based on the outer surface conditions, the boundary conditions. So a great deal of math is used there. So the alternative to radiation is convection. And this is a very messy phenomenon. This is one reason why it's been little studied, is because there are very few solid theories about it. It's mainly based on experimental data, on empirical data. And so we're trying to understand convection from fires. And so think to imagine the complexity here, as we've already talked about fluid mechanics, but you're watching a campfire and the flames are dancing and they're moving, and that's what makes them entertaining to watch. The problem is, how do you predict where those flames are going to go? How do you characterize the distribution or the presence of those flames? And then, since we've been talking about a campfire, but imagine then a wind blowing on it, right? Or fires of different sizes, different flame zone dimensions. Now you say, well, you have to roll all these factors in to some kind of a mathematical model or a physical model that explains how these flames are moving. Now, fluid dynamics, computational fluid dynamics is used, but it's very expensive computationally, right? It takes a lot of computing power to do that. And so that's never going to be practical for rapid field applications, because our computers are just not powerful enough to process these calculations faster than real time. So we need, for a model to be useful in prediction, it has to be many times faster than real time. So we're trying to come up with very simplified representation of this convective heating. And what we find is that even though these flames are moving and they're highly non-steady, there are actually some patterns to those flames. In some configurations, there are some kind of predictable or describable patterns to the flames caused by their buoyancy. And these patterns control things like the frequency of the flames moving out from the flame zone. They actually engage in these little excursions occasionally from the edge of the fire, and they're pushed down and out away from the fire, and they touch fuel particles. And the frequency of those excursions can be described by, but in the frequency domain, it can be described by Fourier analysis or other kinds of analysis of intermittent behaviors, but also the distance that these flames travel. We use a lot of different methods for that, fine thermocouples, or like I mentioned, high-speed videography to capture movements of flames many hundreds of frames per second, you can start to see a lot of these patterns form. So it's not pure turbulence. Sometimes people make an assumption that flames, because they tend to be turbulent for the larger flames, that they're all turbulent, but they're not. In fact, a lot of these structures in the flames are not turbulent structures. They're much more regular and much more understandable than simple turbulence. So convection is a tough problem. The real challenge for us is to come up with simple ways that are physically meaningful, but simple ways to describe the convective heat transfer that is responsible for heating these particles up and raising them to ignition temperature so that the circle of life can continue for fires. And until we can do that reliably, our models are always going to have that weakness. They're not going to be able to represent convection very well. So we study, in order to study convection, we try many different techniques, but one is we study stationary flames. We have gas burners where we create essentially flame zones that are very much like wildfires. We create them with gas burners, and then we can study the flames without having them moving. So we study spreading fires too, those that are moving with the wind or upslope. But the challenge for measuring convection is like weighing a dog while it's running. That's pretty difficult, right? So when you're trying to measure flames for a moving fire, then it's running away from you. You got to make it sit still so that you can take the measurements. And so that's why we contrive a lot of our experiments. They look very artificial compared to wildfires, but they help us understand the processes.
So that was a good analogy, Mark. Weighing a dog while it's moving. That sounds pretty hard. And actually, everything you're doing sounds the research very valuable, and then also and so many things involved with it. It's very intricate as well. Is there anything you'd like to add? Anything we missed?
I think that we need to distinguish between the technology and the science of fire. Okay, I think this is very important. That a lot of times when we think about fire modeling, for example, what we're thinking about is technology. We're thinking about computers and rendering of images and transferring information to people making decisions on fires. But this technology is very important, but it doesn't take the place of good science. We have to spend time understanding the problem before we can produce reliable technologies for modeling it or predicting it or using it as tools. And so I would just conclude with that right now we're focusing a great deal of our efforts on the science, but we haven't lost sight of the technology and about the applied part of this.
All right, Mark, thanks very much. That's Mark Finney, who's with the U.S. Forest Service, and he's studying fire, and he's at the Fire Research Station in Missoula. Mark, good luck with everything. It's very, like I said, it's very important research.
Thank you very much. I've enjoyed it.